Okay, so test is Friday. Test is Friday. I'm going to post the practice problems, and that you'll work on that in recitation. So that'll be a good chance to study tomorrow. There won't be new material, and then I'll also post solutions to the first two recitation assignments. The second of which is due tonight at midnight. So tomorrow sometime I'll post solutions to those first two assignments. What else? Be ready. So what I emphasize in lecture is super important. All the web work, written homework is important, and then the supplementary practice problems. So some of it is similar to like homework questions, and then other is part of it is that you'll have to kind of make some connections, and you'll have to do a problem that's not exactly like one you've seen before. So I'm testing to see if you really understand what's going on. Okay? So when you're studying, try to get out of the mindset of, okay, in this kind of problem, I do this first, like here's the order of things, and here's how I get the answer. Rather, it's like, what am I supposed to understand from this problem? Right? What connections, what connections did I need to make? Right? What did I need to get? All right, so I'm going to test to see if you get it. All right, questions about that? And we'll start, like I said, like 11:45. I'll try to start the exam. I'll hand out Scantrons maybe around 11:40, and then we'll try to get going at 11:45, so you have a full hour to take the exam. Other questions about Friday's test? Okay, yeah, please.
Is the 60-minute timer set? Like, if we arrive late, do we lose time for the exam?
We could stay a little bit later, but yeah. I'm just trying to give more time than 50 minutes. So it's not like let's cut like 60 minutes, hand in your paper, go. Okay, yeah. This one is all multiple choice. But if you just had a sigh of relief, take that back. I write really good exams. I write really good questions that force you to know it. And if you don't know it, you're going to get it wrong. Okay, so whatever kind of format you think is the hardest, study like it's that. Okay, so by multiple choice, it's not like, here's a problem and then here are 4 possible numerical answers. Find the right one. It's going to be different than that. All right. Okay, other questions? Yeah.
Are the tests correct?
If they need to be, don't count on it. So just don't count on it. Pretend it's not. And if it needs to be, maybe, but don't count on it. Other questions? Yeah?
Will we have a homework assignment due on Friday? Is material going to be on?
No. Next homework assignment will be due Monday at 5. Study for the test. Study for the test. Put all your energy into studying for the test. Oh, I take that back. There's a short one that's today's stuff that pertains to the test. So it will be studying for the test, doing that. So yeah, thank you for asking that. So yeah, there will be a shorter web work that pertains to today's material, and that is fair game for the test. Yes, please.
Professor, is the location of the test here?
Here, yeah, we'll be here. Yeah. Any other questions? Okay, so this problem had a slightly lower success. So I think the one thing I'll point out is if the angle, so when you have two planes intersecting, there are actually two angles that are formed. Do you see that? And when they ask for the angle of intersection, they're asking for the acute or the least of those two. So the two angles, they're going to be supplementary, right? They're going to sum up to 180. So you have this angle, say alpha, and then this angle beta. If they're not both 90, then one is acute and one is obtuse. The angle of intersection is referring to the acute angle. So if you work this problem and you get something greater than 90, then the answer to the question will be the supplement or the other angle to get it right. So maybe that was part of the reason why the success was lower on that one. Okay, so I'll let you keep thinking about that. The other one that had some lower success was number 11. Distance from a point to a plane. So we got to think about the tools that we have for that. So what do I when I look at that plane, I know immediately, what do I know? The normal vector, right? The vector orthogonal is 5, 5, 4. And then I have this other point, negative 4, 1, 2, and I'm trying to find this distance. So how am I going to do that? How am I going to find that distance? So could I find a point in the plane? Do you remember how to find a point in the plane? And then I could, if I found a point in the plane, I could make a vector. And then I've got my orthogonal vector. And it'd be really nice to have this cherry green vector. Why? Because the magnitude of that vector would be the answer, right? So I'll let you think about that. So if you can find a point in the plane and make the vector from the point to negative 4, 1, 2, what tool do we have? And this don't just think about it. What tool do we have to get this green vector from this vector, given the fact that I know what the vector orthogonal to the plane is? So I'm just I'm kind of redrawing negative 5, 5, 4 over here now. So that's a hint. That's a hint for that one. But you can think about that and email. So if you're still stuck, you can use the email instructor button. I can try to get back to you as soon as I can. If you give me some details on your progress and your difficulty, I can try to get back to you. Oh, also, I have office hours. I'm going to post this on, I haven't done this yet, but so I'll post this on Canvas, but here's, do I have your office hours right, Jennifer?
Yeah.
So Jennifer and my office hours, oh, I'm switching mine to 1, I'm going to start at 1:30 instead of 1. So it'll be 1:30 to 3 instead of 1 to 2:30. So do 1:30 to 3, but if you want to come a little early, that's okay, I just might be eating in front of you, okay? So some time to eat, but if you don't mind that, you can come a little earlier. So there's Jennifer, and me will be your number one go-to for help. Okay, 116 is Wexler 116, and that's the physical science building. There's like a bunch of tables and palm trees and a crepe cafe. You can order crepes outside, and right by that crepe cafe is the entrance to the Tutor Center 116.
I'm actually in 303.
303. Just kidding. So we'll change that.
Grab a crepe on your way.
Yeah. But it's the same building, right?
Yeah.
So it's Wexler 303? All right, and I am ECA 209 right over there across from that bookstore and computing commons. And then these other student tutors, so also there's student tutors who have had this course before with me, and so there would be also great resources, and they have lots of hours between the two of them. So at STPV, there's Alejandro and Zach, and at least one of them is there in all these hours. And then Ryan Bellis, Alexander Hawkins, and again in Wexler 116, at least one of them is there in all these hours. So you got lots of find time and a person that you like, and get the help that you need. Okay, you're going to need support outside of the class, so please take advantage of that. And I'll post this in modules and as an announcement, okay, on Canvas. Questions on office hours? Okay, let's get at it. We got a little bit to do here today, so let's get started. So we talked about planes last time. So let's talk about, yeah, please.
I just have a question about planes. I found a lot of the web word problems to be really difficult because I wasn't sure what the planes were supposed to look like. So how do you make those sketches, like where you sketch the plane?
I sketched a parallelogram, basically.
Okay.
So
Can it just be any plane? It doesn't have to matter if it's like.
yeah, so you don't have to sketch the plane perfectly in X, Y, Z. You can just do a diagram where everything in your diagram is correct relative to each other, but that whole thing doesn't have to be correct in R3. Does that make sense? So like when I said define the distance from the point to the plane. Well, I just threw the point and threw a plane, and then I drew that.
Okay.
Well, in R3, that plane might be totally different.
That's what gave me a lot of trouble.
Okay, yeah, so when you make these sketches, you're going to have vectors and planes and lines and points. As long as your sketches, as long as all those elements have a good rendering relative to each other, they don't have to be correct relative to the axes. Does that help? Yeah, that's a great point. I should say that earlier when we first, yeah, because pictures are going to be really important in that. And so, yeah, making the planes correct relative to the axes or the line correct relative to the axes is way less important than having a picture where everything is correct relative to each other. Hope that helps. Okay, other questions? Okay, so equations of x, y, and z. We've actually seen two different instances where we ended up with a single equation that had x, y, and z in it. Do you remember what those were? Single equation with x, y, and z, and no vectors in it. No vectors in it, just a single equation of x, y, and z. Planes. And what was said? And we saw something like way in the first week. Spheres. Good. So spheres and planes. So just quickly, what was our equation of a sphere? What was ABC here? What is ABC? Center, right? Is that a point on the sphere? Center? No, it's not. So it's not a point on the sphere. It's the center of the sphere, and then the radius is r. Okay, and then planes. Now what's ABC for this? The normal vector to the plane, the orthogonal vector to the plane, that's what ABC is there. So here ABC is a vector, here ABC is a point. Totally different meanings, right? But both of these situations, we have a single equation of x, y, and z. And because of that, these belong to the same family of things. So equations of x, y, and z, they express all ordered triples in R3 that form what's a general term for what a sphere or a plane is? What are those things? Sir?
Is it a surface?
Surface. These are surfaces. Surface in space. So when you have a single equation of x, y, and z, that will always represent a surface in space. Now, if one of those is missing, it could be just x and z, you still have a surface in space. In fact, we'll talk about those later in class. Doesn't have to have all three, but generically, or just generally, if you have a single equation of x, y, and z, you get a surface. So let's talk about ellipsoids. It's another kind of surface. So here's the equation of our sphere. What we can do to that equation is we can divide by r squared. Then we can allow a different radii on each axis, or different radius, I should say. We should allow a different radius on each axis. With a sphere, you have the same radius in all directions, but if you were to allow for a different radius in different directions, then that would look like this. So like we'd have a radius in the x direction, and a radius in the y direction, and a radius in the z direction. So we're like morphing a sphere, right? We're playing with the how wide it is in different directions. And so what you get is what's called an ellipsoid when you do that. So what kind of things? It's like a rugby ball is like an ellipsoid, or a pill, or a UFO, right? So it's like if you take a sphere and you smush it and you stretch it in different directions, you get what's called an ellipsoid. So here's one example. And so let's make a quick sketch of this. So first of all, we want to make it look like that. I'm done with the green for now. All right, so we want to make it look like that. So we need it to be somewhere here. Oh, it looks like they fixed the screen. Sweet. Or they fixed maybe they moved the camera. Anyway, looks like we can see it all now. So we need x minus 3 squared over something squared. And then we need y squared over something squared. And z minus 2 over something squared. So we need to figure out what those somethings are. And then we have those radii in those directions. So x minus 3 over, with this times 4 is the same as divided by 1/2 squared. Agree? And then divide by 3 squared and 1 squared. All right, so just like a sphere, we have a center, but now we're messing with the radii and the, so let's sketch it here. So where's the center of our ellipsoid? 3, 0, 2. I'm going to come forward 3. Don't go left or right, go up 2. There's my center. And now, so in the x direction, radius of 1/2, so just come forward just a little bit, and go back just a little bit, just in and out of the board there. And those are going to be points, 2 points on the ellipsoid. And I'm going to go, what? To the left and right 3. 1, 2, 3. 1, 2. So those are 2 more points on the ellipsoid, and then up and down, how far? 1, up 1, down 1. So now I got 6 kind of key points on this ellipsoid, and so we'll do our best to sketch it as best we can. Try not to make too much of a mess. So here's the horizontal cross section, which has a x radius of 1/2, y radius of 3. And then we got 2 vertical cross sections. We got this one. And then this other vertical cross section. It's the best ellipsoid I've drawn all day. And so, centered at 3, 0, 2, smashed in the x direction, stretched in the y direction. That's a sphere, starting with a sphere, you're smashing it, stretching it. And so this is another, now we have 3 types of equations. We've got spheres, we've got planes, and ellipsoids. And they all give surfaces. Question on ellipsoid. Okay, so let's talk about other surfaces. There's a way to sketch and identify surfaces that you don't just have memorized by looking at them, and that's through traces. So traces is a way of kind of building a net that reveals what the surface looks like. So don't try to write every word of that. If you want to, do the video later. So by setting one of x, y, or z to different constants, the remaining equations of 2 variables create curves in space called traces that form a skeletal structure of the surface. So I'm going to pick x, y, or z and set that to constants. And then I'm going to get equations of 2 variables, which are like 2-dimensional curves. And then those curves in space kind of form this, like I said, like a net that kind of reveal what the surface is. So we need to have basic mastery of our two curves. So let's just review those. Parabolas have this form. And u and v are any two of x, y, and z. So u and v could be x and z, y and x, to y and z. Okay, so that's parabolas. Circles are like, you know those, that's very similar to C. Again, u and v, any two of x, y, and z. Ellipses, similar to the ellipsoid we just saw. So it's a circle equation with varied radius. Again, u and v could be any two of the three variables x, y, and z. Hyperbolas are like the equation of an ellipse with a minus. And then lines have this form. So this is review, but now it's generically allowing for your two variables to be either xy, xz, or yz. So I'm saying u and v. So in all these cases, you see that I have the minus a and the minus b. What's the effect of the minus a and minus b? So I think maybe the easiest is look at the circle equation. It's a shift, and how does it shift it? So this would be shifting in the direction of u. In the positive direction of u or the negative direction of u? U minus a. Positive, right? So u minus a shifts it a units in the positive u direction. And v minus b will shift it b units in the positive v direction. So translation, shifting. So when we're sketching traces, we have to have these down. Like, so we can sketch these easily in a plane, any of these in a plane. And then we're going to think about those sketches then in R3 as part of forming, they're going to be like curves that lie on the surface. And you get lots of those, then you can figure out what the surface looks like. Does the strategy make sense? All right, so let's go to... this one here. So we are going to investigate by building contour lines. We're going to investigate z equals x squared plus y squared. So first of all, is it going to be a surface in R3? Why will it be a surface in R3? Single equation of x, y, and z. Okay. Is it any of the surfaces we've talked about so far? Is it a plane, sphere, ellipsoid? Doesn't fit the bill, right? So doesn't fit the bill for a sphere, doesn't fit the bill for an ellipsoid, and for a plane, right? So because we have a single variable here that's linear and then equals the sum of two quadratic, that doesn't fit the form of any of what we've seen so far. So let's figure out what this is by doing traces. So what we do is we can like set x equal to, say, different values. So like 1. So we can make like a table here. And then so when we set x equal to 1, what resulting equation do we get? What trace do we get here? We get z equals 1 squared plus y squared. And so we can sketch that. So that's just our, so this is now our plane over here. Now this is the y-axis, right? And the z-axis is up now. So we're looking at the yz plane, right? We're looking at, but this is the yz plane, right? So what x value do we get this trace? And so where is the plane x equals 1? How could you describe where x equals 1 is? Where is it compared to the screen? In front, right? So it's 1 unit in front of the screen. And so in the plane x equals 1, we get the trace that I've drawn over there, this parabola shifted up 1. So that looks like this. So in the plane x equals 1, so that blue curve, that trace, lies on the surface. So I want you to find some more x equal traces. So any that you want, but make it easy on yourself. Pick integers. Certainly it would exist for all real numbers. X equals 8.67, but for our purposes, pick easy integers for x, and then get the corresponding equation, and then we're going to put the resulting trace in that x plane. So let's see here. How about Leveda, did you pick an x value?
Yes.
Tell me. 3? Great. And what curve did you get for x equals 3? Equals what? So I'm going to just flip it around, that's fine. So y squared plus 9. So the curve y squared plus 9, there's 3. It's kind of off my chart here. There's y squared plus 9, and it lives where? Plane x equals 3. So now 3 units out in front of the board, you get the curve y squared plus 9. Who's got another good one? Yeah.
I had one, x equal, you can have x equal -1, it would still be z equals 1 plus y squared.
So yeah, -1 is going to end up with the exact same trace that we had for 1. So you get the same parabola, y squared plus 1, but now that lives in -1. What about just x equals 0? What do you get? Z equals y squared. Yep, z equals y squared. So that lives in the actual yz plane because x equals 0 in the yz plane. So you do this many times, and you get a bunch of parabolas, right? So this is y equals 1, there's x equals 1, x equals 2, x equals 3, x equals -1, -2, -3. So even just with traces from x, you already get a feel for what the surface is going to look like. Okay, so now let's do it for z values. So set z, you get some slightly different here. So rather than setting x equals different values like I'm showing with these blue curves, now take some different values for z and find the curves that you get for varying z values. So you should have seen for positive values of z, you get circles, right? Let's turn off. So here's c equals 3. C equals 4 is circle with radius 2. C equals 4 gives a circle with radius 2. Where does that live? So where would that circle live? In z equals 2. So where did it come from? It came from when we picked z. If you pick z equals 2, you get the equation x squared plus y squared equals 4. No, 2. 4.
Yes, it would be z equals 4. That would give us the radius 2.
Z equals 4. I'm saying z equals 4. So that's going to live in z equals 4. Why isn't it living there? Where are you?
Is it the c slider?
No. It should be this one. Oh, because maybe it's too far. Oh. What the heck? Maybe it's this one. No. I don't know why it's not working. But this should be seeing planes with the circles in them. I don't know why it's not working. Well, that's a shame. Okay, so anyway, c equals 4 lives in the plane. Z equals 4. 4 equals x squared plus y squared is the circle with radius 2. It lives in the plane z equals 4. So then as your z increases, your radius increases. So these are the different circles you get. What about when you choose a negative value of z?
It can.
It's impossible in the real numbers, right? So if you pick a negative value of z, you don't get any equation. Therefore, it doesn't live down there in the negative z. All right, so we got all these. So these are for different values of positive z values. And then we could turn on those again. And so just with a few x and a few z traces, you get a very good idea of what this thing looks like. It's like a, three-dimensional parabola kind of, which is called a paraboloid. So as soon as you get enough traces that make a fine enough net, your brain fills in the rest, right? And so you can just see that it looks like this. Right, so that is too dark. But I can fix that. Is there a light one in there somewhere? Is that better? Transparency on? Transparency. I don't know. Is there a light? Is there something light in there? About there? I don't know. Okay. Okay. So this is a paraboloid that we built from scratch by finding traces, right? Setting one variable equal to several values and getting the corresponding curves in those planes in R3, and then making a net of those curves. Any questions? Okay, so paraboloids. So which way does this paraboloid open? In which direction does this open or expand or get wider? Positive z direction, and notice the equation. That's our linear variable, right? So the linear variable will be the direction of the axis of the direction that it opens. Okay, so let's then summarize paraboloids. So setting x or y equal resulted in traces that were parabolas. Setting z equal to various constants results in traces that were circles. And then, so just, we'll talk about this more later, but z traces have a special name. They're called level curves because you're staying at a constant level. If you pick z to be constant, then you're staying at a certain height or level. So a level curve is another word for a trace for a constant z. All right, so we've got a bunch more practice here. So there's three ways that we can manipulate a paraboloid. We can change the variables, we can shift it, and then we can stretch an axis, like instead of having circular paraboloid, we can have like elliptical paraboloid where you've stretched an axis. So we'll just quickly go through these. So let's take just a couple minutes. So you want to identify the vertex, direction of opening, and then whether it's circular or elliptical, and maybe a little more description about that. Like if it's elliptical, then how is it elliptical? In which way is it longer or shorter? So for each one of these, is it where's the vertex, which direction does it open, and then is the paraboloid circular or elliptical? So just a couple minutes, get a partner and talk through. Go.
Yeah, it really zooms in. And then it should be circular too, because that's sort of constant.
Yeah, it's open in the wide direction.
Everyone's talking to somebody. There's not enough mouths moving.
Yeah.
You have a partner.
It's fine for
Figure them out.
it's fine for it's fine direction. Sorry.
So like on the stuff we go, you go like that.
You're answering these 3 questions about all of those.
So on like the first one, I guess it's really cool.
It's whatever the first one is. Positive stretch.
Yeah.
The vertex would be
Vertex is also zero.
yes. This one's not basic. And then circular. Circle.
So I guess only 2. Yeah, vertex is like 18.
Because let's say say that y is only 2 values that can give y equals 0. Yeah, 2.
So just the one on the top right was
Say that's negative x.
I don't know. And then we shifted one up. So it would be.
So open.
Oh.
So, okay. First one is no, we use yeah, no, we use
You can do x hat. You can write x direction or write I vector. Don't use x hat.
I've seen other books saying X.
But that's not what it doesn't. That doesn't mean what we're trying to do. Okay, so let's quickly go through them. So the vertex for these first 2 is the origin. No shift, right? No translation. Okay. What direction did this one open? Opens to the right. Opens to the right, right? What direction did this open?
Towards the board.
Into the board. So it's gonna the vertex is gonna be the origin is gonna open behind, moving behind the board. It's gonna open up away from the board behind. Okay? And then anything else? Circular or elliptical? Both circular. Okay, what about this one? What direction the vertex is at? Origin opens which way? Up. Opens up. Circular or elliptical? And so it's going to be elliptical. It's going to be wider in x or in y? Yeah, so what is, this is like a radius of 3 for x and a radius of 1/2 for y. So a lot wider in the x direction than it is in the y direction. So quickly, something like, not my best work, but the point is it doesn't have to be great artwork, just good enough to communicate what it is, right? So stretched a lot in the x direction and actually smushed a little bit in the y direction from a circle. Okay, this one. Vertex. 1, -2, 4 is the vertex. It opens which way? Towards you, right? Out from the vertex is at 1, -2, 4, and it's going to open coming at you, right? In the positive x direction. Circular, elliptical? Circular, right? We're not messing with any radii here. So this one has a center of -1, -3, 2. Or sorry, vertex. And it opens in what direction? To the right. It's going to open to the right, positive y direction. Circular, elliptical. And wider in which direction? Wider in the z direction. So these ellipses will have, they'll always have a proportion of 5 to 4 z radius to x radius, right? So 5 to 4 as they get bigger. The proportion will be in the ratio of 5 to 4 z to x for those radii. Questions about these? Okay, one more topic. We can do it. We can do it. So we've got planes, spheres, ellipsoids, and paraboloids so far. So there's another class of surfaces called cylinders. And when you think of a cylinder, what immediately comes to mind?
Circle.
Yeah, like a can, right? And that's wrong. Okay, that's wrong. That is a type of cylinder, but that's not an all cylinder. So here's what a cylindrical surface is. You can start with any surface with a constant cross section in some direction along the surface. So it doesn't have to have a circular cross section. The kind of cylinders that we use in everyday language are the ones that if you cut them, you get a circle every time, right? But really, any surface that you can cut and get the same thing every time is a cylindrical surface. Doesn't have to be circular. So you can take any planar curve and you just translate it in the direction normal to the plane of that curve, and you're creating a cylinder. Start with any planar curve and translate it perpendicular to the plane of that curve, and you'd be sweeping out a cylinder. So the most basic cylinders that you can get are the ones where you have an equation of 2 variables and you're graphing it in R3. So when you have an equation of 2 variables and you graph it in R3, you get a cylinder. So y equals x squared is not a curve in R3. Why? Because z can be anything, right? So what would you get? So first of all, we can draw y equals x squared in the xy plane. And which way does that open? On which axis does that open? Y equals x squared? Positive y-axis, so it might look something like this. But now z can be anything. So it's not a curve anymore, but a surface. So can you imagine what if you translate this for all values of z, basically? Do you see what you get? So you get just like a curved sheet, right? A curved sheet that's vertical. So what about z equals cosine x? Z equals cosine x. So here's z equals cosine x. So here's the zx plane. This would be x here and z. I just turned the axes, so I'm looking at x this way and z this way. So there's z equals cosine x. And so, but in R3, y could be anything. And so, just let that translate in the y direction. And that's a cylinder. That's called a sinusoidal cylinder. That wavy yellow sheet is a cylinder because I started with a curve and I just translated that curve perpendicular to the plane of the curve. And so that's the cylinder z equals cosine x. Okay, so what about, can you sketch, how about z equals e to the minus y? Can you imagine or sketch that as a cylinder in R3? Z equals e to the minus y. See if you can sketch that without technology, So here's the zy plane, and there's that curve in the zy plane. Z equals e to the minus y. And so then to get the cylinder in R3, imagine extending that along the x direction. And so now we just added like a gazillion surfaces to our repertoire, because you can start with any curve in any of the two planes and extend it in the other variable, and you've got a surface. So that's what a cylinder is. So we can have a circular cylinder, that's fine. Start with a circle, and you get like a tube or a pipe. But for our purposes, a cylinder means any curve extended, swept, to form a surface. So this is an exponential cylinder. You got an exponential cylinder there, sinusoidal cylinder.